January 17th, 1940, Wilmington, Delaware. The winter air hung cold and still over the Nemours Building as dawn broke across the DuPont headquarters. Inside a third-floor laboratory, the scent of coal, tar derivatives, and formaldehyde mingled with steam from coffee cups that had gone cold hours ago. Dr. Wallace Carothers stood before a tangle of glass tubing and condensers, watching a viscous polymer drip into a collection flask. His hands trembled slightly, not from the cold, but from exhaustion. He had not slept in 36 hours. Outside the window, America was waking to another day of uneasy peace. Still 2 years from a war it did not yet know was coming. But in that laboratory, in that precise moment, a revolution in chemistry was solidifying into something that would fall from the sky over Normandy, Burma, and the Pacific atolls. Something that would replace the ancient luxury of silk with the modern promise of industry. Something called nylon. The fiber that formed in that flask on that January morning was not merely a chemical achievement. It was a declaration of independence, not political, but material. For centuries, America had bowed to the silkworm, to the mulberry groves of China and Japan, to the complex biology of insect larvae spinning their cocoons in controlled environments half a world away. Silk had dictated terms. Silk had been expensive, scarce, temperamental. And when war finally came, when young men would leap from aircraft into hostile skies over Europe and the Pacific, silk would prove to be something far more dangerous than expensive. It would prove to be vulnerable to embargo, to blockade, to the whims of geopolitics. But nylon belonged to chemistry, to factories, to the controlled violence of American industrial capacity. Nylon could be summoned from coal, air, and water. Nylon answered to no emperor, no silkworm harvest, no monsoon season. Yet, on that January morning in 1940, nylon was still just a promise. A material so new that only a handful of chemists understood its molecular architecture, so revolutionary that its creators could barely imagine the world it would create. To understand what happened in that Wilmington laboratory, one must first understand what did not exist in 1938. America had no synthetic fiber that could match silk's strength and elasticity. The nation's industries relied on natural materials, cotton, wool, linen, and above all, silk, for parachutes, for surgical sutures, for women's stockings, for the delicate insulation in electrical equipment. Silk was irreplaceable. It came from the cocoons of Bombyx mori, the domesticated silk moth, which had been cultivated in China for more than 5,000 years. The process was labor-intensive, requiring careful temperature control, precise timing, and vast quantities of mulberry leaves. A single cocoon yielded approximately 1,000 yards of continuous silk filament, but it took nearly 3,000 cocoons to produce a single pound of raw silk. The United States imported 90% of its silk from Japan, and by 1937, that dependency had become a strategic liability. Japan's invasion of China in 1937 disrupted global silk production and sent prices soaring. American textile manufacturers watched with growing alarm as their supply chains tightened. The U.S. military, which had been using silk parachutes since the early 1920s, faced a particularly acute problem. A single parachute required approximately 20 yards of silk fabric, lightweight, strong, and able to withstand the violent shock of deployment at terminal velocity. There was no substitute. Cotton was too heavy and absorbed moisture. Rayon, the first semi-synthetic fiber, lacked the necessary tensile strength and degraded when wet. The military had stockpiles, but everyone understood those stockpiles would not last through a major conflict. And by 1938, as Hitler annexed Austrian Chamberlain flew to Munich, the prospect of major conflict no longer seemed distant or theoretical. Into this anxiety stepped Wallace Carothers, a chemist of unusual brilliance and unusual melancholy. Born in Iowa in 1896, Carothers had earned his doctorate at the University of Illinois and joined the DuPont Company in 1928 to lead their fundamental research program in polymer chemistry. DuPont gave him something rare in American industry: freedom to pursue basic research without immediate commercial pressure. Carothers was not asked to invent products. He was asked to understand the fundamental nature of large molecules, the mysterious polymers that formed the basis of natural materials like rubber, cellulose, and silk. For years, Carothers and his team synthesized experimental compounds, probing the boundaries of what was chemically possible. They created the first synthetic rubber, neoprene, in 1931, but Carothers was chasing something more eleganter: fully synthetic fiber that could rival the ancient perfection of silk. The challenge was molecular. Silk's strength came from its structure: long chains of protein molecules aligned in parallel, held together by hydrogen bonds. To replicate that strength synthetically, Carothers needed to create long-chain polymers with similar properties. Through years of methodical experimentation, he and his colleague Julian Hill discovered that under the right conditions, certain chemicals would link together into chains of extraordinary length. In February 1935, they synthesized a polyamide molecule formed by linking together units of adipic acid and hexamethylene diamine that could be drawn into a fiber stronger than any synthetic material previously created. Carothers called it fiber 66 because each of its two constituent molecules contained 6 carbon atoms. DuPont called it a miracle, but miracles require engineering. The leap from laboratory curiosity to industrial product consumed for years and $27 million, astronomical sum in the Depression era. DuPont built a massive production facility in Seaford, Delaware, where coal, air, and water were transformed through a series of chemical reactions into the raw materials for nylon. The process was complex and unforgiving. The polyamide had to be melted at precise temperatures, extruded through spinnerets, small plates pierced with hundreds of tiny holes, then rapidly cooled and stretched to align the molecular chains. The resulting fiber was thin as spider silk, strong as steel wire, and elastic enough to absorb tremendous shock without breaking. And unlike silk, it was entirely immune to the biological whims of silkworms, monsoons, and mulberry harvests. Nylon was industrial. Nylon was American. Nylon was controllable. DuPont announced nylon to the public on October 27, 1938. At the World's Fair in New York, the company positioned it as a revolution in women's fashion, a new word in textiles. They proclaimed, though they carefully avoided explaining exactly what nylon was made from. The first nylon stockings went on sale in May 1940, and 4 million pairs sold in the first 4 hours. Women lined up outside department stores, desperate to own a piece of the future. The stockings were sheer, durable, and far less expensive than silk. They became instant icons of American modernity, symbols of a nation that could conjure luxury from chemistry. But even as women admired the new stockings, the U.S. military was conducting very different tests. At Wright Field in Dayton, Ohio Army Air Corps engineers were dropping test dummies from aircraft, watching carefully as experimental nylon parachutes deployed and descended. The tests were promising. Nylon proved slightly less elastic than silk, which meant it absorbed shock more harshly on deployment to problem engineers. Addressed by modifying the canopy design, but it was stronger, more resistant to mildew and rot, and above all, it could be produced in virtually unlimited quantities on American soil. By late 1940, as the Battle of Britain raged and America began to prepare for the possibility of war, the military made its decision. Nylon would replace silk for parachutes, and DuPont would gear up for war production. Then came December 7, 1941. Pearl Harbor changed everything. Within weeks, the United States was engaged in a two-ocean war of unprecedented scale. The demand for parachutes became staggering. Paratroopers, bomber crews, pilots, cargo drops, every branch of the military needed thousands upon thousands of parachutes. In February 1942, DuPont ceased all civilian production of nylon. Every ounce went to the war effort. Women who had queued for nylon stockings were asked to sacrifice, to make do with rayon or go bare-legged, to understand that the same material that had graced their legs was now saving lives over hostile territory. And they did. The nylon stocking became a symbol of wartime sacrifice, hoarded and treasured, darned and repaired far beyond the point of reasonable wear. On the black market, a single pair could fetch $20 more than a week's wages for many workers. But women understood. The nylon was in the sky now, woven into canopies that blossomed white against the clouds. American paratroopers of the 82nd and 101st Airborne Divisions trained with nylon parachutes throughout 1942 and 1943, preparing for jumps that would become legend. They learned to trust the synthetic fiber with their lives, to leap from the shuddering bellies of C-47 transport planes into darkness and flak and the unknown. When they jumped over Sicily in July 1943, when they descended through chaos over Normandy on June 6, 1944, when they dropped into the frozen hell of Bastogne in December, they fell beneath nylon. The fiber performed exactly as the chemists had promised. It did not rot in tropical humidity or freeze brittle in sub-zero cold. It did not tear easily or tangle impossibly. It arrested their falls with reliable, reproducible force, turning suicidal velocity into survivable descent. By the war's end, American factories had produced more than 1 million parachutes, consuming tens of millions of yards of nylon fabric. The industrial achievement was staggering, but it masked a quieter tragedy. Wallace Carothers, the melancholy genius who had given America its synthetic silk, did not live to see his creation save lives. Carothers had struggled with depression for years, haunted by doubts about his scientific contributions despite his obvious brilliance. On April 29, 1937, at age 41, he checked into a Philadelphia hotel room and drank a solution of potassium cyanide mixed with lemon juice. He died within minutes. His death came less than 2 years before nylon stockings conquered America, less than 5 years before nylon parachutes filled the skies over Europe. Carothers never knew that his polymer would be produced by the billions of pounds, that it would reshape global industry, that it would help win a world war. He died believing himself a failure, unable to see the revolution he had authored. But the fiber remembered what the man could not. Every nylon parachute that deployed over enemy territory carried within its molecular structure the ghost of Carothers' achievement, the patient, methodical exploration of polymer chemistry, the willingness to pursue understanding without guarantee of application. When DuPont awarded him a posthumous patent for nylon in 1938, the document credited him with inventing a synthetic linear condensation polymer capable of being formed into fibers. The language was technical, bloodless, precise. It could not capture what the invention actually meant for the Japanese soldiers who watched American paratroopers descend over the Philippines in 1945. Nylon was incomprehensible. Japan had entered the war as the world's dominant producer of silk, expecting that its control of this strategic material would provide significant advantage. Japanese parachutes, made from domesticated silk, were excellent light, strong, reliable. But they required silk, and silk required silkworms, and silkworms required mulberry groves, and mulberry groves required land and labor and time. By 1943, as American submarines strangled Japanese supply lines and strategic bombing destroyed industrial capacity, Japan's silk production faltered. Parachute silk was diverted from military use to more critical applications. Japanese paratroopers made do with inferior substitutes or no parachutes at all. Meanwhile, American factories, powered by cheap coal and hydroelectric dams, fed by rail networks that spanned a continent, staffed by women who had left kitchens and classrooms to work lathes and looms produced nylon without limit. The Americans conjured parachutes from air and chemistry. It was a kind of magic that Japan, for all its martial discipline and industrial skill, could not counter. The contrast was ideological as much as material. Japan's war machine ran on tradition, rice and silk, on Bushido codes and emperor worship, on structures that had evolved over centuries. America's war machine ran on innovation on factories that could be retooled in months, on chemists who could synthesize substitutes for any natural material, on an industrial philosophy that treated nothing as irreplaceable. When America needed rubber and Southeast Asian plantations fell to Japan, American chemists synthesized rubber from petroleum. When America needed aluminum and bauxite was scarce, American engineers developed new extraction techniques. And when America needed silk and Japan controlled the supply, American industry simply eliminated silk from the equation. Nylon was not a substitute, was an upgrade, a material superior in almost every practical way to the substance it replaced. This capacity for reinvention, for creative destruction and rapid adaptation, was something authoritarian powers could not match. They could discipline armies and sacrifice populations and conquer territories, but they could not teach chemists to ignore orthodoxy, could not encourage engineers to question every assumption, could not create the intellectual freedom that made genuine innovation possible for the American soldiers who fought beneath nylon canopies. The fiber became a talisman of industrial providence. They did not think about polymer chains or condensation reactions. They thought about the reassuring rustle of fabric, the sharp tug of deployment, the blessed deceleration that meant life instead of death. But they understood, in some inchoate way, that the parachute represented something larger than itself. It represented a nation that could invent its way out of problems, that possessed resources so abundant and flexible that even the sky could be conquered through chemistry. When they landed in French fields or Pacific jungles and bundled their parachutes for recovery and reuse, they were handling more than survival equipment. They were handling proof that American industry could manufacture miracles on demand. The symbolism extended beyond the battlefield. Back home, the absent nylon stocking became a daily reminder of the war effort, a small sacrifice that connected civilian life to military necessity. Women drew seams up the backs of their bare legs with eyebrow pencil, maintaining the illusion of stockings because the fashion mattered, because maintaining normalcy mattered, because the appearance of abundance mattered even in its absence. And they understood that their sacrifice was temporary, that when the war ended, the nylon would return not scarce and expensive, but abundant and cheap, flooding department stores in quantities that would have been impossible with silk. This was the promise of synthetic materials, of industrial chemistry, of American productive capacity. Scarcity was a problem to be solved, not a permanent condition to be endured. By 1945, as victory approached, DuPont was already planning the post-war world. The company had learned to produce nylon at unprecedented scale, driving costs down through continuous process improvements. Engineers had developed new applications: nylon rope, nylon tire cord, nylon brushes, nylon gears. The material that had been introduced 7 years earlier as a luxury textile had become a fundamental industrial commodity, as essential as steel or concrete. And when peace finally came in August 1945, when the last paratroopers landed and the last parachutes were bundled and stored, DuPont pivoted back to civilian production with stunning speed. Nylon stockings returned to stores in 1946, and the pent-up demand was ferocious. Women lined up by the thousands, sometimes rioting when supplies ran short. The nylon riots of 1945 and 1946 became legendary, otherwise orderly shoppers shoving and clawing for stockings. Police called to restore order outside department stores. It was absurd and understandable, a release of years of denial and sacrifice. A hunger not just for stockings, but for normalcy, for luxury, for the material proof that peace had truly returned. But the stockings were only the beginning. By 1950, nylon production exceeded £100 million annually, and it continued to climb. The material infiltrated every aspect of American life: clothing, carpets, upholstery, industrial parts. It became so ubiquitous that its revolutionary origins faded from memory. Within a generation, few people remembered that nylon had been invented specifically to replace silk, that it had been born from strategic necessity, that it had once been a cutting-edge wonder. It became mundane, ordinary, a material so common that its presence went unnoticed. This was, perhaps, the ultimate triumph: not fame, but invisibility. The seamless integration into daily existence that marks truly transformative technologies. The military continued using nylon parachutes long after silk vanished from the supply system. The material proved itself through decades of jumps in Korea, in Vietnam, in peacetime training exercises and special operations. Modern parachutes use advanced synthetic fibers like Kevlar and Spectra for specialized applications. But nylon remains standard for many uses, still performing the function Carothers polymer was designed for more than 80 years ago. Every airborne operation, every pilot who successfully ejects from a damaged aircraft, every cargo pallet that floats safely to Earth, owe a debt to that January morning in Wilmington when a troubled chemist watched synthetic fiber drip into a collection flask. The story of nylon is often told as a tale of corporate innovation, of DuPont's foresight in funding basic research, of America's industrial might. These narratives are true but incomplete. The deeper truth is that nylon emerged from a specific historical moment when material dependence collided with geopolitical reality, when the ancient luxury of silk became a strategic vulnerability, when American chemists were given the freedom and resources to question nature itself. Carothers did not set out to make parachutes. He set out to understand the fundamental architecture of large molecules, to probe the boundary between natural and synthetic materials, to see if human ingenuity could replicate what evolution had perfected over millions of years. That as polymer happened to arrive just as the world needed an alternative to silk, that was timing, fortune. The strange alchemy of historical necessity meeting scientific readiness. And perhaps there is a larger pattern here, a rhythm that repeats through the history of American innovation. The pattern is this: strategic dependency creates urgency, urgency creates investment, investment creates freedom, freedom creates innovation, and innovation eliminates the original dependency entirely. It happened with rubber, with aluminum, with petroleum, with rare earth elements. It happened with nylon. A material that did not exist became so abundant that scarcity seemed impossible. An empire that controlled silk lost its leverage overnight when chemistry rendered silk obsolete. This capacity for material reinvention, for taking the question, what do we do when we can't get X, and answering we make something better than X, has been a hallmark of American industrial power since the 19th century. It is not inevitable. It requires institutional support for basic research, tolerance for failure, freedom to challenge orthodoxy, and capital willing to invest in long-term uncertain payoffs. These conditions are rare and fragile. They can vanish through complacency, short-term thinking, or ideological rigidity. Carothers would not have described himself as a participant in grand historical forces. He was a chemist who suffered from depression and self-doubt, who published meticulously researched papers on polymerization mechanisms, who supervised a small team of researchers in a corporate laboratory. He did not live to see B-17 crews bail out over Germany and descend safely through flak, did not see paratroopers mass behind enemy lines, did not witness the nylon riots or the post-war boom. But his polymer did all those things. The fiber carried his intellect forward into history even as the man himself disappeared into tragedy. There is something almost unbearably poignant in this gap. The creator gone, the creation triumphant. The world transformed by an invention the inventor believed was insufficient. On June 6, 1944, when 13,000 American paratroopers jumped over Normandy in the pre-dawn darkness, every one of them descended beneath a nylon canopy. They landed in hedgerows and flooded fields, in German positions and French villages, scattered across kilometers of hostile territory. Many were killed before they landed, shot by ground fire or anti-aircraft guns, slaughtered in the chaos of the drop. But thousands survived, rallied, fought, and accomplished their mission. Those survivors owed their lives to many things: training, courage, luck, the sacrifices of comrades. But they also owed their lives to chemistry, to a polymer invented in a Delaware laboratory by a depressed genius who never saw a war. When they touched French soil, they carried with them proof that American science and industry could bend nature to necessity, could conjure strength from petroleum and coal, could make the sky itself a highway for liberation. The Japanese silk producers, watching their strategic advantage evaporate as American factories pumped out unlimited synthetic fiber, must have felt a peculiar vertigo. They had spent centuries perfecting row culture, breeding silkworms for maximum production, cultivating mulberry groves across the islands, spinning cocoons into thread with extraordinary skill, and in less than 5 years, American chemists had rendered all that expertise irrelevant. The ancient craft could not compete with modern chemistry. Biology could not match industrial synthesis. This was the cruelty and promise of technological progress. Traditions that had sustained communities for generations could be obsoleted in a single patent cycle. The silkworm farmers of Japan did not disappear immediately. Silk remained valuable for certain applications, retained cultural significance, continued to be produced in smaller quantities. But silk never again dominated parachute production, never again held strategic importance, never again commanded the prices that had once made it a cornerstone of Japanese exports. Nylon had broken that monopoly permanently. And what of the silkworms themselves? The Bombyx mori that had served humanity for 5 millennia, that had been so thoroughly domesticated they could no longer survive in the wild. They continued spinning cocoons in climate-controlled facilities, producing silk for luxury garments and specialty applications, oblivious to their diminished strategic importance. They did not know that their ancient partnership with humans had been demoted by a synthetic rival, that the thread they produced from mulberry leaves had been matched and exceeded by a thread produced from coal tar. The silkworms simply did what evolution had programmed them to do, transforming leaves into fiber with elegant biological efficiency. But in the contest between biological efficiency and industrial scale, industry won decisively. Nylon factories did not need mulberry groves or climate control or careful harvest timing. They ran continuously, day and night, producing fiber as long as raw materials flowed and power remained on. This was the advantage of synthesis, reliability, scalability. Nature could not compete. In the decades after the war, nylon became so successful that it generated its own problems. The material was too durable, too cheap, too abundant. Landfills filled with nylon products that would not degrade for centuries. The same molecular structure that made nylon ideal for parachute strong, chains resistant to breaking, made it an environmental nightmare. Rivers and oceans accumulated nylon fishing nets and fabric fragments. Microplastics from degrading nylon worked their way up food chains. The triumph of synthetic materials created new forms of pollution that natural materials had never posed. This was the cost of industrial victory, the shadow side of abundance. Silk degrades naturally, returning its protein molecules to the carbon cycle within years. Nylon persists, a testament to human cleverness and a burden on ecosystems that never evolved mechanisms to break down synthetic polymers. The story of nylon is not cleanly heroic. It is complicated, ambivalent, shadowed by consequences that Carothers could not have foreseen and DuPont did not anticipate. Yet for all its complications, nylon remains a genuine achievement, a moment when human ingenuity expanded the boundaries of what materials could exist. Before nylon, the universe of possible fibers was limited to what biology could produce: cotton from seed hairs, wool from sheep, silk from larvae, linen from plant stems. After nylon, the universe of possible fibers was limited only by chemistry, by imagination, by the ability to design molecules with desired properties. This expansion of possibility is what makes the story of nylon more than a wartime anecdote or a corporate success story. It is a marker of transition, the moment when humanity began to seriously manipulate matter at the molecular level, to become not just users of materials, but designers of materials. Everything that followed: Kevlar, Gore-Tex, carbon fiber, smart fabrics, programmable polymers, traces its lineage back to that Wilmington laboratory where Carothers coaxed long chains from simple precursors on a quiet morning in January 1940. When Dr. Wallace Carothers watched his polymer solidify in a collection flask, he was watching the future take shape, though he could not have known it. The fiber in that flask would multiply into billions of pounds, would fall from aircraft over 5 continents, would clothe legs and reinforce tires and upholster furniture and perform 10,000 unglamorous functions. It would save lives and create pollution, would liberate American industry from dependence on Japanese imports and contribute to the post-war throwaway culture of plastics. It would be simultaneously a triumph and a warning, proof of what humans could accomplish through science, and proof that accomplishments generate their own complications. But in that moment, in that laboratory, the polymer was simply a solution to a problem: how to make a fiber as good as silk without needing silkworms. The solution worked, and because it worked, the sky opened for airborne warfare. The store shelves filled with affordable luxuries, and the ancient dominance of natural fibers began its long decline into specialty status. If Carothers could return now and see what his polymer became, would he recognize it? Would he claim pride in the parachutes and the stockings, the ropes and the carpets? Or would he mourn the environmental burden, the microplastic pollution, the downstream costs of his creation? We cannot know. He left no testament, no hint of how he imagined nylon's future. He left only the polymer itself, the patents, the laboratory notebooks, and a final act of despair that closed his eyes before the story truly began. Perhaps that is the tragedy: not that he died, for everyone dies, but that he died not knowing that his work mattered desperately, immediately, historically, not knowing that men would trust their lives to the molecular architecture he designed, not knowing that his name would be remembered not as a failure but as a pioneer who gave humanity a new kind of thread, one that required no worm, no cocoon, no ancient craft, just chemistry, just understanding, just the patient, methodical exploration of what carbon and nitrogen and hydrogen could become when arranged with intention. The parachutes that fell over Normandy were woven from this understanding, and they carried more than soldiers. They carried the weight of human ingenuity, the promise that material limits could be transcended through knowledge, the demonstration that a nation with sufficient scientific freedom and industrial capacity could invent its way past seemingly insurmountable obstacles. This was the lesson that Japan and Germany learned too late: that the true strategic resource was not silk or oil or steel, but the institutional capacity to generate innovation, the cultural willingness to question authority and try impossible things, the economic surplus to fund research without immediate return. America possessed these advantages in 1940, not because Americans were inherently superior, but because American institutions happened to align in ways that permitted risk and rewarded curiosity. Carothers was free to explore polymer chemistry because DuPont was willing to invest in basic research. DuPont was willing to invest because American capital markets rewarded long-term innovation. Markets rewarded innovation because property rights and rule of law made returns predictable. These enabling conditions were not destiny, they were choices, made and sustained through decades of policy and practice. And because these choices aligned, when the strategic need arose, the innovation was ready. The parachute opened. The soldier lived. The war was won, not by nylon alone, of course. Wars are won by production and strategy, by courage and sacrifice, by 1,000 interlocking advantages that compound over years of conflict. But nylon was one piece of that advantage, one strand in the web of American material superiority. And that strand began with one chemist, one laboratory, one flask of polymer that did not exist before human hands called it into being. This is the power and responsibility of science, the power to create materials that nature never imagined, and the responsibility to understand what those creations will unleash. We are still learning the lessons of nylon, still grappling with the synthetic world we have made, still trying to balance the abundance we have achieved against the pollution we have generated. The thread that saved lives in 1944 will persist in landfills until 2444. A legacy both glorious and troubling, a reminder that every solution creates new questions. But on that January morning in Wilmington, those questions lay far in the future. In that moment, there was only chemistry, only the patient work of understanding, only the quiet satisfaction of seeing theory become reality in a collection flask. The war that would give nylon its purpose was still 2 years away. The silk that nylon would replace still came reliably from Japan. The paratroopers who would trust their lives to the new fiber were still civilians, unaware of the uniforms they would wear or the skies they would fill. Everything was still to come. But the thread was ready. The polymer waited, coiled in its molecular perfection, prepared to serve a future it could not anticipate. And when that future arrived in fire and necessity, when the world needed a miracle, American chemistry delivered. Not a miracle of faith or magic, but a miracle of understanding, of science applied with precision and manufactured with scale. The miracle of seeing what nature provided, understanding why it worked, and building something that worked better. This is the thread that changed the sky, and the sky has never been the same.